Okay, so you're supposed to come prepared with your questions over the review for the exam, which I have up here. So we'll just entertain questions. Where do you want to start? I don't think we have time to do them all. It's a pretty long review. So if it may be parts of every one you want to see, but you maybe don't need to see all the parts. But as much as we can, we'll skip those parts. Sometimes you have to have the answer to get to the next part. But
Can you go to number 3?
Number 3, okay. So number 3 says, the following SAS output created by running a model selection routine in ProcReg on various data sets with 6 predictor variables. These are not necessarily all from the same data set, so consider each step in isolation. Right? So in other words, don't think that step 3 is relating back to step 2 or whatever, because I won't necessarily make them off the same thing. It's like, can you look at this step and figure out what should be done? Right? So using a stepwise method with alpha equal 0.1 to enter and stay in the model, what, if any, action would be the result, I guess that's what that says, at each of the following steps. Okay, so at step 1, you get an F value and a P value for every variable. So all 6 of the variables. If any of them are significant at the alpha 0.1 level, you're going to enter a variable into the model. And then how do you choose which one to enter?
High step value.
You pick the lowest p-value, but here there's quite a few of them that all say less than 0.01. So in order to tell, well, which one's really the lowest, you have to look at the F value. So you're going to pick the biggest F value, which is 63.77 for x2. So variable, yeah, let me just put that, clear up. Variable x2 is entered. And any removed? Well, this is step 1, so I'm Xing it out. It looks like I'm putting a variable. So, okay, how about that? None get removed. So then we'll go to step 3. And again, this is not, there is no step 2 here because these are considered in isolation. So at step 3, we have some variables already in the model. It looks like x1 and x2 are already in. But just whatever variables are already in the model, here are the remaining variables to be considered. And so what's the decision? X6 has a p-value of 0.04, and none of the others meet the criteria to be entered. And so X6 would be entered. And then we don't have the information to see if any are removed. What would that information be?
If X6 rented in the model and then X1 or 2
Right.
became higher than the p-value.
Exactly. So then you get the output for once X6 is in there with X1 and X2 to see if any of the 3 get kicked out. You know X6 won't get kicked back out immediately. That would be impossible, because if it were, it wouldn't go in, because this is the p-value it will have in that model. But the other 2 may have lost their significance when this one comes in, so you check to see if any get removed. But we can't do that here. So go to step 5 as the next part of this. And statistics for removal. So again, these aren't necessarily the same model or even the same data set. So you just say, well, I've got 4 candidates to go into the model, into whatever's already there. And we've got 2 of them that are tied, but then the biggest F value is 22.2, which is X6. Oh, I'm sorry, I didn't read that. You're right. Statistics for removal. So you want to remove what? Yeah, so when it's statistics for removal, then these are the ones that are in the model. And X2 is no longer significant. So X2 would get removed. Am I on the right line?
Wouldn't that be the right though? Variable x2 removed, not variable x2 entered. Yeah, none are entered because they're all.
Oh, right. X2 removed. And then X3 and X5 are candidates to go in, but neither one of them is significant at the 0.1 level, so none entered. None entered, one removed, so guess what? You're done. Right? So you know the routine would stop at that point. Okay? So there's number 3. Next question. Number 5, all right? I'm going to scroll a little bit and see if I can. There we go. So the following analyses were conducted on radial keratotomy data collected in a study. The dependent variable is the 5-year post-surgical change in refractive error. And the variable is CHG_RE. 2 predictor variables were baseline refractive error, base RE, and baseline curvature of the cornea, base CRV. Right? Examine the SAS output and write out the model. So when you're supposed to look at SAS output to write out the model, you're looking to see what variables are in it and what the parameter estimates are. So they're not wanting the one with the Greek letters here, they're wanting the one with the numbers in it, right? So the model. So we'll scroll down to the model, or to the output. So here is the parameter estimates from the model. So I forgot what our dependent variable is. What are we predicting here?
The change,
Change in refractive.
I thought the refractive error is one. No.
The baseline refractive. Yeah. So the change in refractive error is equal to. So we have an intercept of 12.36. I'm not going to write all the decimals here, and then minus 0.2916 times base refractive error, and then minus 0.2204 base curvature.
Would it be change or refractive error at?
Yes. Thank you. All right. So that's part A, write out the model. Now I got to scroll back up to see what part B was. Compute the predicted value, the residual, the studentized residual, and the deleted studentized residual for the first observation on the next page, which has a base refractive error, I'm just going to call it base, of negative 0.675 and a base CRV, I guess I need to use the RE, base CRV of 46.25. Okay, so to get the predicted value, we can already do that without having to look at the next page. But so the predicted value of change, you just plug these values in. You guys should be really good at this by now. Right? So what do you get?
I got 4.13482.
4 point what?
13482.
13482. Okay. And then we are also supposed to get write your answers in the blanks provided in the output in the next page. So then I can just scroll to there and see what we're supposed to compute. Okay, so this is y hat. That number is going to go here. Residual, that should be fairly easy.
1.24018.
So read it to me again.
1.24018.
Okay. And now what about studentized residual?
Student is the observed residual divided by the standard error of the residual.
Okay. So the studentized residual is 1.24018 divided by the standard error of the residual. Did they?
Or is that R student? I think R student might be.
R student is a deleted residual.
Okay.
Right.
That observation deleted, right?
Yeah, and I'm hoping that I was kind of cutting and pasting different problems together, so hopefully I gave you all the output you need to actually compute that here, but we'll see. The standard error of a residual, do we have everything we need for the standard error of the residual? Right, so let me just write that here out. Standard error of residual. So for now, these are not deleted, so we're okay. But what's the standard error of a residual? You remember that formula? Hint, it had the hat value in it. Standard error of the residual is S sub E times the square root of 1, is it a minus? Yeah, minus the hat for that observation. So that's on the bottom. So they didn't give us SE on this page, but what is SE? The root mean squared error. So we got to scroll back up to get that, but let's fill in the hat while we're here. They gave us the hat value of 0.12668. So square root of 1 minus 0.12688.
You said SE is just root and that's
Oh,
right?
66. I got this wrong. Yeah, S sub E is just root mean squared error. Okay, so let's scroll up, see what that was. Root mean squared error is 1.10817. So 1.10817. So that goes on the bottom of the fraction. On the top is the 1.24018. Assuming Taylor gave us the right number, which is kind of scary, but yeah. All right, so what do you get there? 1.19 what? 8? Okay. So then the studentized deleted residual, the one that SAS calls R student. Remember how to do that one? Let's come over here, kind of on scratch paper. The book labels that R with a subscript in parentheses of I. So meaning deleted, the ith observation deleted.
It's yi minus y hat over the s. Well, the root going to see with that observation deleted.
Right.
The times the square root of 1 minus the hat value.
Okay, so all of it is really the same except for that. You need the root mean squared error when that guy is deleted. Now that's what I was worried. Did I give you that?
SI is root mean squared error with that pointing it out.
Right. Let me scroll down real quick and see if I... No, apparently when I was cutting and pasting, I didn't paste that analysis with that one person gone. But you would have to get that. We could actually cheat and get it here. How could you figure out what S... No, you couldn't. Because it's a different guy. I was going to say you could go to the next row where they give you that value and back solve, but that'd be back solving for the S sub 2 instead of the S sub 1. Right? And they would change. They wouldn't change much, but they would change. So that one I can't give you, but on the test Wednesday, I would, if I wanted you to be able to compute that, I'd have to give you more output. Okay, and that's it for there, right? So I did not, on that one, ask you to compute a hat value, but I know you had to do that in your homework. Where do you get hat values? You have to have the matrix, the hat matrix, and it's the diagonal of the hat matrix, right? So either you have to be given the hat matrix or you have to be given the x prime x inverse matrix, and then you take the vector and the transpose of that vector and do all that stuff. But okay? What about Cook's D? How would you compute a value of Cook's D?
1 over k plus 1 times the hat value.
Okay? So DI for Cook's D is, you said it and I was...
1 over k plus 1.
Yeah, 1 over k plus 1. And then the hat value over 1 minus the hat value. Then times r squared sub I. And r squared is the studentized residual that we computed a minute ago. Right. So what is K? Number of what? K is number of variables in the model. So we got 2 in the model, so this will be 1 over 3. And then the hat value for this first one, let's just see if we get the right answer. So this will be 1 over 3. And then hat value is 0.12668 over 1 minus that. And then the residual, I wrote it under here, but this is R sub I. And I didn't write it with that notation, but this is R sub I, studentized residual. So 1.198 quantity squared. All right, so somebody give me that number.
0.0694.
Okay. Doesn't quite match what SAS has. They have 0.06932, but we're rounding to 4 places, 5 places on things, and so there's some round off error in there. But okay, so this particular problem did not ask you to compute Cook's D, but you very well. Is there any other question on here that makes you do that? I don't remember, but be prepared to do that, certainly.
the CV for jackknife?
Jackknife is the old book's way. The guy who first published the studentized deleted residual named it the jackknife residual.
Oh.
That's what it was called.
All of this is making more sense.
Yeah. And the old book used that term, the jackknife residual. You know what a jackknife is, right? A penknife that folds in on itself. And for some reason, they made an analogy with folding it in on itself, and that's like doing that. You know, but I'm not sure how I see that's like doing that, but anyway, they called it the jackknife residual.
So that's just the deleted.
What's that?
Which one is that again? Sorry. Jackknife
Is the deleted studentized residual. It's our student. So this one is student on the output. This one is our student. There are a few things in the statistical literature that are like that, where they use some word for something. Like my favorite is the bootstrap estimator, right? And that's a really common thing. We're going to bootstrap this. And bootstrapping is a way of resampling from within the sample you took to get an estimate of standard error and all that kind of stuff. And the guy who first thought it up and published the paper on it said, well, it's kind of like pulling yourself up by your own bootstraps. You got your data, and you're going to use your data, and you're pulling yourself up by your own bootstraps. He called it the bootstrap estimator. So. And now that word's used all the time. Nobody really knows why, but that's why. Okay, so now CV for critical value. Basically, what are the cutoffs for these things? So what's the cutoff for both of the types of residuals?
Deleted if T credit for the student. Which one do you want? Like, because you said the deleted model or the one with an N?
Well, let's do the studentized first. The only difference between these two is 1 degree of freedom different, right? So what are the degrees of freedom on that one? It's the error degrees of freedom in the model, right? So it's n minus quantity k plus 1. And then when you delete a subject, your n goes down by 1. So this one has 1 degree of freedom less than this one. But unless you have really small samples, it isn't going to make any real difference. And SAS really kind of ignores that and just basically flags it if it gets above 2. So, what about Cook's D? What's the critical value for Cook's D?
If it's greater than the gap percentile, that's percentile.
Yeah, our book does it a little bit different. There's almost 2 critical values. There's one where if you're below this, you're fine. And then one up here that says if you're above this, then you're in trouble. And in between is like, you decide. Right?
The other one should be greater than 1.
Well, and that's what I said. Our old book said, or actually this book says it too, says you can use this F percentile, or you can, some authors say to use 1. Just use a cutoff of 1. And that's kind of typical. You remember what SAS is doing? 4 divided by n, right? And I didn't really teach that, but when you're looking at the SAS output in the graphics that it uses, it uses 4 over n, which flags a lot more things than either of the other things would do. But so you're going to do it's high if greater than F statistic and which percentile? The notation our author uses is F sub 0.2, which is the 80th percentile, right? So 80th percentile, and the degrees of freedom are...
Wait, I thought our book said if it's less than the F with the bracket of 0.8, so 20th percentile it was okay. And if you get above the 50th percentile, then you...
Yep, you're right. You're right. I was remembering that they had 20th percentile as the bottom you're okay thing, but it's the yeah, they write bracket 80, which is the 20th percentile, right? Because the bracket is upper tail of that area. So if your F distribution, it's a skewed distribution, looks kind of like that. If you got 80% in the right tail, then that's the 20th percentile. So if you're down there, you're fine. But if you go to the 50th percentile, which would be about right in there, so this is F bracket 50, the median of the F distribution. If you get above that, you should flag it as something you need to look into. Right? Now, what are the degrees of freedom of this F? You remember that? The error degrees of freedom is the denominator, but you also need k plus 1. So this is k plus 1 and n minus k plus 1 degrees of freedom, right? So this is the F bracket 80, and I had that wrong, is the 20th percentile. So you're low if less than that. High if greater than F bracket 50 with the same degrees of freedom. Okay, what about hat values? What's the cutoff for? No, that's the Cook's D. The other way of doing it is Cook's D. You worry about if it's bigger than 1. But for hat values, it was what? 2 times the mean of the hats, so H bar. And again, some authors say no, you need to go out to 3, but we use 2, so high if HII greater than 2 times H bar. The mean of all of the hats. So do you remember what the mean of all the hats is? What do the hats add up to? They add up to k plus 1, right? And then there's n of them, so the average is k plus 1 over n. So this is 2 times k plus 1 over n. All right, we've got 2 variables in this model, so that's 3 over n. So this is 6 times 3 over n, or 2 times 3 over n is 6 over n. And what is our n? 54. Right? So 6 over 54 is equal to what? What did you say? 1/9? So 0.11 repeating, right? And the reason I want it as a decimal is that's the way SAS outputs it. So when I scan up that column, I'm just looking for ones that are bigger than that number. So I got to go up to the top to see the hat is in the last column. There's one. Oh yeah, the one that's highlighted I ignored. Right? So the very first one is a little bit bigger than that 2. It would not be bigger than 3 times it. And then 0.15, the one right below it, the one right below that. There's a bunch of these that are going out for the hat. Okay? Is that enough from that problem? I guess there's some examine residual plots from this problem. Okay, this is one of the x variables, the baseline refractive error, and then studentized residual without current observation. So this is our student on the y-axis. You see any weird points?
The top right one.
Yeah, this is a little weird, isn't it? It's not weird variability-wise, but it's certainly an outlier. Right? So you can see that, oh, baseline refractive error, I've got one that's a positive 2. Everything else is negative 2 or below. That seems odd. Does anybody know anything about optometry to know about refractive errors? Well, here's the same thing. These are predicted values for the change in refractive versus change in curvature. I forgot. It's refractive error, right? Yeah, change in refractive error. That's our y variable. So this is predicted value, y hat, versus the residuals. And that is the same point. It's sticking out there. And it's predicting a value of 2 for that one, and everything else is 3 or bigger. Well, if I scroll back up to the data, it's somewhere up near the top. There it is. That row right there. Look at the baseline refractive error for that one. Positive 2, and everything else in this whole data set is negative. Right? And what it turns out is that that was a data entry error. And they entered a negative. They entered a positive 2, and it should have been a negative 2. A refractive error for this kind of eye surgery, radial keratotomy, which is an old. Do you even know what that is? It's kind of gross, really. But you know what LASIK surgery is, right? It's the same. It treats the same thing, right? It treats nearsightedness, and so your refractive error is always negative in those kind of people. So to have a positive is not possible. You wouldn't do surgery on somebody with a positive refractive error. Right? They would be farsighted. But anyway, the radial keratotomy, they would take a scalpel and they would make these slits in your cornea radiating out from your pupil. Right? Now they just take a laser and they shave it off. Right? Well, what happened when they did that, it actually worked. They would slice it, and then it would heal back, and the scar tissue would tighten it up, and it would flatten out the curvature of the eye a little bit. Right? So, yeah. But what they found was that when people got up to high altitudes, then that would it would mess it up somehow, and because of the air pressure was different, and their vision would they basically go legally blind when they got up to high altitude. So pilots and things like that, they get up there and all of a sudden they couldn't see. So yeah, that'd be fun. But I like this example because it shows you that you can't trust your eye to skim through a huge page of numbers and pick out an odd one. But you start looking at plots and you start looking at hat values and things like that, and you realize, oh wow, there's one of these that's weird, right? And it makes it, and that's what the whole reason for all this is. Yep.
So if you were looking at data yourself, would you go ahead and correct that to a negative, or would you just delete the entry?
As a statistician, I would call the scientists on the project and I'd say, hey, you got a value here that looks like to me it ought to be a negative 2. Can you confirm that? If they say, no, I can't confirm it, I don't know, I have no way to go back and remeasure that person, then you delete it. Right?
So you said you saw that. Can you show me how you saw that was a positive 2 and how you just said that there's no way?
It was flat. We saw it in the residual plots.
Right.
Right? The one you pointed out, that point up there to the right, I'm looking down here.
Okay.
This is baseline refractive error. You probably can't read that, but that's what that is. And so I see, well, there's a point way over there by itself, so its refractive error is a 2. And then you start noticing, well, there's 0. Everything else is negative, and that one is a positive 2. So then you just start, then you go in the data and eyeball and try to find it. And usually you use SAS to do that too. You say print if greater than 0, and it pops out all the positives. Right?
So how did you know on the third one it was the same one?
I just remembered where it was. I remembered it was up close to the top. So And you can see from this that it's the only one in there that is positive. But right. So Kevin, to finish your question, sometimes the data management people on a project will have a license to do self-evident corrections. Right? If it's really obvious what this is, then you don't have to send it to the site, make them sign it, and all that. But that's technically, it's called an audit trail. If you're going to change the data, you have to show why you changed it and when you changed it and who changed it and all that, right? Because this stuff's going to regulatory authorities and they don't like you changing data. So, okay, next question.
So is that the only one that you see on all three of those graphs?
Yeah, I never did actually finish answering that question. That's about the only point that I see that I would be real concerned about. Everything else looks like just random scatter.
How did you know the one on the third graph was the same as the one on the first graph?
It just has to be.
Okay.
Right? But if you look at the predicted value, that's y hat. Right? And so that has a y hat that's a little bit less than 2. And you can go up to that one row again in the raw data and look at the y hat values and see that, yeah, that matches up. So it's y hat. Oh, I didn't print y hat here, did I? No, there it is.
1.98.
Yeah, 1.98. So a little bit less than 2. And all the other ones are 3 or bigger. Right? And notice the hat value. I didn't really talk about it, but we pointed at it and said that one's above the cutoff for the hat value. But look at it compared to all the others' hat values. There are others that are out, like that one, but they're not out near as far as that one. And if we did 3, what's 3 times h bar? It'd be 9 over 54, right? Instead of 2 times, I get 3 times 3. So what is 9 over 54?
1.6.
Which is 0.166 repeating. And this is 0.26. So it's way out there. None of the others make it to 3. There's one that's close, 0.15. It's not quite at 3, but I don't think there's any others that were at 3. And I'm only showing here those 3 residual plots, but if you just run it in the new version of SAS, it gives you all those different graphs to look at, and you'll see one that has leverage values, and you'd see a really huge spike there on that one. So it would flag it for you, basically. Yep.
So when we were talking about the Cook's D value, you said that it was low if f sub bracket 0.8. Does that mean that you should ignore those with that value as well, or does that, or the way I first understood you to talk about it was that below the f at the 20th percentile was really good, and then above that there was a gray area, and then above 0.5 was
right. So in this graph down here, don't be concerned.
okay.
Up here, you definitely want to go look at those values and see if there's something weird about them. In the gray area, they're basically saying that's your choice, that's your call.
Okay.
You might want to check any in there, but you know, it's up to you.
And so again, we're just supposed to look and see if there is anything weird with the data. Like on the homework, there was that one guy who his kneeling height was all like the 1920s, and that was just for that one observation. So you know if there's an error in collection. But if you can't see an error in collection, then still keep it?
That's a great question, and the answer is there is no answer to that. It's a case-by-case basis, right? So if that person had turned in one value like that and the other 4, then you wouldn't know that, you know, it wouldn't be so obvious it was a measurement error. And you'd say, well, I don't know. And you say, well, I'm going to check on it, and you check the source data, if possible. Say, can you go measure this person again? Because that number doesn't seem right. But a lot of times it's what we call lost to follow-up. It's too late. We don't even know who that person is anymore. It's just gone. Then if it's that bizarre and you know that can't be right, then you just delete it. So
then the same is true with it. If it only violates one of these criteria, but not all of them, that's an up to you decision. But how many does it have to violate before it's like you should?
Yeah, and really, there's no answer to that question either. It's always an up to you decision as the team. You're rarely doing this stuff all on your own. There's going to be scientists involved that produce the data and all this stuff. So you say, hey, here's what I've identified as being potential problems. What do you think? And some people are real conservative and just kick them all out, and other people are like, I don't want you throwing away data, and so then it's sort of a what do we think as a group? What are we going to do here? So
like when you look at stuff, if you guys remove an observation, do you still have to record the observation when you remove?
Mm-hmm. Absolutely. Yeah.
So then you just
Yeah, exactly. Yeah, you never throw away an observation from a data set. You just don't include it in your analysis, right? So it's in the spreadsheet or whatever. So like we submit stuff to the FDA, they can see it and they can agree with us or not that, yeah, you were justified in deleting that observation from your analysis, but they want to see everything collected. So. Okay, what about the logistic regression problem here? There's two of them, right? This one is the one that you can do by hand. So give the conditional proportions for smokers for each gender, compute the odds, compute the smoking odds ratio using females as reference group, and then give the logit form of the model using Greek parameters, and then using the data in the table, compute those parameter estimates. And we did one like this in class, where you can do the whole thing all by hand. Right? Any questions on how to do that? Yeah.
See, when you say females are the reference group, does that mean they're the denominator?
Yeah, they're the denominator. Yeah. And that's typical that the lower numeric value is what SAS is going to use as the reference group. So whichever one you want to be referenced, you make them the 0. Right? So no questions on this?
Part D, I don't know what to see.
Okay, D is using Greek parameters to specify the model. So this is gender and then whether or not they smoke, right? So we're trying to predict the probability somebody smokes based on their gender, right? So the logistic regression model, what's on the left-hand side? Log odds, that's right. Natural log of the odds of smoking. So I'll just say odds of a 1 for the Y variable. And then the right-hand side, by transforming to the logit, right? This is called the logit or the logit transformation. By transforming to that, then we make just a regular linear model out of this. So it's your regular old beta 0 plus beta 1 times gender or sex, and there's your model. And then when you plug in part E, compute the parameter estimates, you'll need all these intermediate parts to get to that, right? But let's say, well, let's do it this way. If the subjects are females, what's their model? Log odds equal beta 0. Right? So then to get your estimate of beta 0, you find the odds for females, you take the log of that, and you got your beta 0 estimate. Right? Now, what's odds for female? How do you get that?
E to the probability, the
Yeah.
odds that they're,
We'll just do the
Yeah, I'm starting the other way and coming down.
Probability divided by 1 minus.
Okay, probability, I'm going to put sub f, probability for females, over 1 minus p sub f, and then you just get that out of the table. So you look at females, what's the probability they're a smoker? 28 out of 208. So even just using fractions, this is 28 out of 208 over 1 minus 28 over 208. And then that gives you your odds. Then you take the log of that, and you have your beta 0 estimate. And then you do the same thing with males. And to get this beta 1, the log odds for males is beta 0 plus beta 1. Right? So you get the log odds for males on this side, like this, but using the male row. You now have an estimate of beta 0, so you subtract it from both sides, and you have your estimate of beta 1. Has anybody got it all the way worked out?
I got negative 1.861.
For beta 0? Negative, say it again.
1.861.
861.
And then 0.461 for beta 1.
And then beta 1 equals 4 point what?
0.461.
0.461.
your odds ratio is just e to that p1, right?
That's right. So the odds ratio, which I'll call capital R, capital O, capital R, is, and this is females on the bottom, they're the reference group, is just E to 0.461. Okay?
So if males are the reference group, then they would be 0.
Right. You'd make males the 0.
Hey, wouldn't you have to add in the beta?
This number is not this number. This is after she's solved. Did anybody have the log odds for males?
0.2465.
0.2465, and then you plug this number in there and add it to this number, and you should get that number.
Oh wait, my log odds. Sorry, that was the odds. The log odds is negative 1.400.
Oh. Say it again, negative
1.4
1.4004.
004.
Okay? So this is beta 0. This number plus beta 1 is this number. So then add 1.8 to each side. And this is the difference between those two numbers. What is this odds ratio after you take e to that power? 1.585. And you could also get that easy enough for this problem just by going back to what your odds were and taking the ratio of them. You should get exactly the same number.
So it's saying males are 1.585 times more likely?
Exactly. Males are 1.585 times more likely to smoke than females are. Yep. I was just working on some data for a client, and we had the reference group set up a certain way, and they thought that, and the number we got was like 0.64 for the odds ratio. And they're like, 0.64? I don't know what that means. Well, you're 0.64 times as likely, which means there is a 36% reduction in your likelihood of. Can you flip? And finally, I convinced them. They didn't know to flip it over, take the reciprocal. I said, well, if you do it the other way around, then it would be whatever the reciprocal of 0.6 is, like 10 divided by 6.
1.5625.
Yeah, 1.56 or whatever. Then they understood that. Oh, 1.56 more times more likely if you're in this group than that group. That they liked. So then we reran the analysis and flipped it all to use the other reference group, and everybody was happy.
So you just realize that it's less likely.
Yeah, and I agree with them. This is harder to interpret. Mathematically, it's not. Us mathematical people understand, no problem. But the general public, they understand 1.5 times more likely, but they don't understand 64% as likely. That what? It throws them a little bit. But. Okay. Do I have a more complicated logistic regression thing? Yeah, here we go. So this is one where you can't do it by hand now. You have to rely on SAS or something to run it. Write out the logistic regression model which was fit. Compute test statistic and p-value for determining gender is important. Compute odds ratio and 95% confidence interval. Compute predicted probability. And we did one of those right at the end last time, but we ended up just sort of accidentally picking one that was too easy because it was the reference group on everything. So it was just the intercept term. But any questions on how all of that is done? Okay, we got plenty of time. So part A, write out the logistic regression model that was fit. I won't do that one, but here's the parameter estimates. It's just going to look just like that with beta 0 plus beta 1 times the first one plus beta 2, and then you're just going to fill in what those beta values are estimated to be. Right? Then this is using dummy variables for race. So I have Asian, Black, Native, and other. So my reference group is white. And it's blanked out the odds ratio for Asian. How do I get it? Odds ratio for Asian. And that's odds ratio of Asian compared to whites. That's exactly what we did there. So the odds ratio for Asian is e to the negative 0.440. What's that? Alex, you punching numbers? 0.6. Say it again. 0.644036. Okay. It's just accident that that's the same number I happened to use as an example over there a minute ago. But okay, so that's the odds for Asian. So what is this telling me?
There's 64%.
They're only 64% is likely to do this being hospitalized as white people. Okay. What about confidence limits? I don't remember if we even got to that in class. Did we do confidence limits?
Same thing.
Almost, but there's an extra step. But same thing you always do for confidence intervals. You start up here, right? You've got the parameter estimate, standard error. These are chi-square, which are normal, right? You take square root of a chi-square, you get a standard normal. So you're going to use your 1.96 thing.
I think I know this.
Yeah?
It's E to your regular confidence.
Exactly. You're going to get the regular confidence limits on the parameter estimate. Then you just take E to the endpoints of the interval, and you got the endpoints of your. So the parameter, so the confidence interval parameter. So parameter confidence interval B sub j, whichever one you're doing, plus or minus 1.96 or whatever per confidence level, but it's almost always 1.96, times the standard error of B sub j. So for Asians, that's negative 0.44 plus or minus 1.96 times 0.5237. So give me that interval.
The plus is 0.586452.
0.586452. Is that what you said?
6452. Yep.
Okay. And the minus?
Is negative 1.46452.
Negative 1.4, and you got to do it again.
1.466452.
Okay. And that's lots of decimal places, but there's a comma right in there. All right. Now, what Alex said, to get the confidence interval for the odds ratio, you just exponentiate the endpoints of this.
That's the bottom one is 0.23074.
23074.
Is 1.7975.
1.7975. Okay?
What is this data testing?
This is comparable for the odds ratio of Asians compared to whites on the odds of being hospitalized. Right? This number looks like there's quite a bit of difference, right, between Asians and whites. But what is this telling me?
It'd be still in there. One is still in there.
One is in this interval, right? So remember, a confidence interval, the interpretation is we are 95% confident that the true odds ratio is somewhere between these two numbers. Since 1 is in there, a ratio of 1 means they're the same. So the odds might be the same for Asians as it is whites. So we do not have a statistically significant difference. Look at the p-value for Asian. 0.4. Right? So you cannot reject that they are the same.
How do you find the chi-squared statistic?
I'm glad you asked that because I was going to forget to do that. Let's look at the gender one is the one that we're supposed to compute, right? So we've got I'll use B sub G for gender. Okay, so B sub G is 0.8861 and S standard error of B sub G is 0.1844. So the test statistic is always computed how?
B0 divided by standard error.
Right? The B divided by its standard error. So that's going to be a Z. And it's a Z here, not a T. The only thing I can tell you why is because T, to be T, it has to come from a normal distribution, and that's for linear regression. This is maximum likelihood estimation, and it's normally distributed, not T distributed. There's not much way to say it other than that, and that's why they go to this walled chi-square thing. But I'll show you that in a second. So 0.8861 divided by 1844 is
4.8053.
4.8053. Now, just looking at that, before we try to do a p-value, big, small, or not so much? That's big. That's huge. We're going to get a really small p-value, right? This is 4.8 standard errors away from the null hypothesis. Now, if I square that number, what do you get? 0.091. That is the walled chi-square. Right? So, just to prove it to you, do the one right below it. Take 0.44, divide by 0.5237. And then square it, and you should get 0.7060. Okay. Now, so you can get the p-value now, it's been blanked out as well, from either of these two. This one's chi-square with 1 degree of freedom. So you have a chi-CDF function on your calculator. Or you can do it from a z, this as a standard normal distribution. So what do you put in for your lower? That's a good question. You got normal CDF from this number to infinity. 8.3 to infinity, 9999. And then you don't have to enter 0, 1 because it is standard normal. The calculator will default to 0, 1 if you leave the close your parentheses right there. Right? 7.7 times 10 to the negative 7. There's a lot of 7s in there.
Chi-squared is 1 degree of freedom.
Right. Chi-square has 1 degree of freedom. If you take a standard normal and you square it, you get a chi-square with 1 degree of freedom. Then if you take a sum of those squares, then you get the degrees of freedom of how many you summed up. Right? All right, so let's do the x squared CDF on your calculator. From 23.091 to infinity with 1 degree of freedom.
I got 1.4 times 10 to the negative 6.
If you're not getting exactly the same thing, it's because of the round-off error. Right? If you take this many decimal places and then square it, you'll get more decimal places here. And that's...
We rounded off quite a bit from that squaring it.
Yeah, there's a lot of round-off error in here. But if you think about it, they both have the same exponent, so you're accurate to the 8th decimal place, right? No, 7th decimal place. You're accurate to the 7th decimal place. So it's not that much round-off error. It looks a lot different because it's 5 point something instead of 7 point something. But you got to remember there's 6 leading zeros before you get to that.
So irrelevant.
Yeah. Okay. What else do we have to do on this one?
This is a likelihood ratio then? Oh.
The overall model test is a likelihood ratio test, but these are walled chi-square tests when you break it down. But so this likelihood ratio is the overall. This is equivalent to the F statistic in a multiple regression. The top F is the overall model. That's what this is. Testing the global null hypothesis that all the betas are 0. So, all right. Now, I think the only thing left to do, let me look back up here. Compute test statistic, p-value for gender. We just did that. Odds ratio, and did that. Confidence interval, and then now compute the predicted value of being hospitalized for a 30-year-old white male and a 47-year-old black female and compare. Yeah.
It's supposed to be 2 times that normal CDF. That's why.
Ah.
Yeah.
Good catch. I forgot that. Yeah, this is 2 times that because it's a two-tailed test, right? It's a two-tailed test. So 2 times that, and then that gives you, does that give you the other one?
Yeah, it gives it exactly the same thing.
Okay. Thank you. I didn't even think about that. But. So well, that tells me that this number did change. The other one wasn't -7. It must have been -6.
Yeah, it was negative 6.
Okay. Okay, well I heard, would it really change the number? But I was thinking this number out front, but you were saying the exponent. Yeah, that's off by 10, so a factor of 10. Okay, now let's do this. Compute the predicted probability of being hospitalized for a 30-year-old white male and a 47-year-old black female. All right, so this half of the room does the 47-year-old black female. This half of the room does the 30-year-old white male. And I'll scroll back to the output so you can see what the parameter estimates were. This is a several-step process, isn't it? You were supposed to write it down when I said it. You have it printed, right? 30-year-old white male. I think that's right. And then you guys were 47-year-old black female.
Females or males?
Females are the reference group.
Blue or white male?
Yeah, so females are the reference group. Males are when sex is equal to 1.
Sorry, 1 is female. Other way around.
Wait, 1 is female?
I'm going to scroll up there because now I'm not trusting anybody. Okay? So it says 1 is female, 0 is male, and then the race categories are dummied in, so that's always obvious. So 1 is yes and a 0 is no. Okay? So let's go back down to the model parameter estimates. And you start by predicting log odds, then you get odds, then you get probability, right? So this is the 30-year-old white male.
Okay, alright.
The
log odds or the
log odds is negative 3.2023.
3.2023?
Yeah, negative 3.0 or 20.
302.
You have right.
Negative 3.2023.
Okay. So then the odds
are 0.04. Yeah.
So that's exponential of that is what? Point
Only decimals.
0.040669.
04669.
0.0669.
Like that. Okay. And finally, probability.
0.040669 divided by 1 minus that.
1 plus that.
Or 1 plus that.
When you go from odds to probability, it's a plus sign on the bottom. When you go from probability to odds, it's a minus sign on the bottom. And the only way I can ever remember is I got to write out the equation and solve. Oh yeah. So it's 0.040669 divided by 1 plus that. So I'm just going to write 1.04069. And it's going to be right around 4%. Now, while you guys are computing that, give me the 45-year-old black female.
It's negative, the log odds is negative 1.733.
Okay, wait. Log odds is what?
Negative 1.733. That, then find the odds, it's 0.17675.
Okay.
And then that divided by 1 plus that gives you 0.1500.
15020. Okay, has anybody got this one?
It's 3.9%, so 0.039008.
3908. Okay.
It's a 47.
47? Yeah, thank you. 47-year-old black female compared to a 30-year-old white male. More likely to get hospitalized. About 5 times more likely. Well, 3, not quite 5 times, but. Can I do ratio of their odds? Sure you could, right? The odds ratios that are printed out here are one variable at a time, changing by 1 unit. So for age, 1.014 means if somebody is 39 compared to a 38-year-old, they're 1.014 times more likely, right? Now that doesn't seem like it's much bigger than 1, does it? But is it significant? Sure. Look at the confidence interval. It excludes 1. But remember, that's for a 1-year change. That's not much change. If you take a 10-year change in age, then you can actually multiply this by 10. You get a 0.1 and go through the whole process. And you can do odds ratios for a 10-year increase. You just have to do them by hand.
That's what I was thinking. You said to sum them all up, the differences. Like that, you definitely multiply that by what, 17 at age.
Yeah. Yep. So you can take the odds ratio here. We got odds for this female. We got odds for this male. Take this number for me. 0.17675 and divide by 0.040669. 4.355. So this person is 4.35 times more likely to be hospitalized than this person.
And is that going to be your odds ratio?
And that is an odds ratio. It's just not the typical odds ratios that get output here because you're varying all variables at once and by more than 1 unit.
Would it be, like, would that be the odds ratio you come up with if you did all that by hand? Like,
yes. Yes. Yep. Mathematically, it would work out the same.
I like that right there.
Yeah, it's a lot easier. Okay, there was a part D, but I don't remember, or part E. Use the output for the model with race variables and the model fit statistics without race and compute a test for the joint importance of race as a predictor variable. And I didn't teach you that, so we'll skip that. That won't be on the test. Oh, yes. Before you take off, Kristen emailed me. She was looking into data for projects and found somebody that you know, right, said that there's Kansas data available publicly from KDHE, which is Kansas Department of Health and Environment, and what were the other places?
Any status-related experiment.
Okay. Yeah, by the Freedom of Information Act, all that publicly collected data, if taxpayers funded it, it's out there on the web. So if you're... What's that? Yeah, there's any kind of study that they've done, that data's out there. So the challenge is finding it, but if you do web searches, KDHE data, then you probably hit like a repository of different things that you can get your hands on. Yeah. Yeah. Oh, I forgot to turn this on.